then you just lose some points. But in general, you cut out something from these flag varieties, and this is something very singular. So say in case S is trivial, Bx is the Springer fiber. And it is known to be equidimensional. Of dimension 1/2 of codimension in the nilpotent cone of the orbit of this nilpotent element. Okay, so in other words, the Springer resolution is strictly semi-small. Okay, the dimension of fiber over some orbit is exactly 1/2 of its codimension in the whole nilpotent cone. And now you intersect those singular Springer fibers with those smooth but disconnected. Maybe I should add that this is connected. See, maybe I should mention that there is a Weil group representation in the top homology of this Springer fiber for any x. And essentially, well, this is a construction due to Springer, and maybe we'll not talk about it, unfortunately. But essentially, it gives all reducible representations. It only works as stated for GLN. I mean, there the nilpotent orbits are numbered by partitions, right, by Jordan blocks, and the Weil group is the symmetric group. Reducible representations of symmetric group are also numbered by partitions, and they are exactly here. For other groups, it doesn't work as smoothly. I mean, these representations are sometimes reducible, and there is no bijection between nilpotent orbits and irreducible representations, but essentially doing the same thing as we're doing now, you obtain all reducible representations exactly once. So let's come back to what we're doing now. We'll consider this component group of the simultaneous centralizer of our nilpotent and semi-simple and nilpotent elements, and certainly it acts on the Borel-Moore homology of the simultaneous fixed point set, and we can decompose this Borel-Moore homology with respect to isotypic components of this group. So we set the irreducible representations appearing in this homology space. Okay, and we can do similarly in this example when S is trivial. Yeah, then BSX is just the Springer fiber. Again, there is the component group of this centralizer. This will be just the centralizer of the nilpotent element X, and it also acts here. So X is trivial, S is trivial, only X remains. And then again, not all the irreducible representations of this component group appear in the top Borel-Moore homology, but if we decompose this top Borel-Moore homology with respect to the action of this finite component group, then all the multiplicity spaces are irreducible models over the Weil group, and this way you obtain all the irreducible representations of the Weil group. Okay, maybe let me formulate it, but we will not discuss this theory, unfortunately. All the irreducible W appear exactly once as the multiplicity space chi where chi is the relevant irreducible representation of the group, of the component group. Okay, and essentially what we do now is some variation of this theme of Springer. Okay, so in Springer there was just one. Sorry, there is no semi-simple element in Springer theory. There was just one nilpotent, and now we add a semi-simple element, and we do the same thing, and we essentially recover representation theory of the affine Hecke algebra. So let's go back to the affine Hecke algebra. So we had this central reduction. H sub A of the affine Hecke algebra. And here A was a semi-simple element. In our group, that was the product of the semi-simple group G with dilations, multiplicative group. So A was of the form S and T. T was just a complex number. And then X was an nilpotent element fixed with respect to A. Okay, so it means that the adjoint action of S on this X just multiplies by T. Okay, and now we're after representations of this central reduction, and we'll start just geometrically the central reduction acts on the Borel-Moore homology of this simultaneous fixed point set. And it commutes with the section of the group component. And in particular, it acts in all the multiplicity spaces of this group component. So we take one relevant representation. Relevant means that chi actually appears here. Not all the irreducible representations of the component group appear in this homology space, but some do, and we take one, and we set the standard module K of S sorry, x chi. So A is essentially the same as S. This is just the multiplicity space, so it's home over this component group from chi to the homology space. Okay, and this we did last time, as far as I remember, and then we started defining co-standard modules and did not quite succeed. So to this end, we choose some slice to our nilpotent orbit. So we take the centralizer of S. It acts on the whole nilpotent cone, and in particular on the fixed point of this element A. And we take an orbit of X. Okay, and we take some slice and this is some naive slice in classical topology, analytic and local. It's not something like Luna slice from invariant theory. So S, a slice to this orbit, well, through X. In classical topology. So in particular, and it's a local slice. So it contracts to X. Okay, and we take its pre-image under the Springer resolution map. So S tilde, it contains the pre-image of X itself, and this is just the fixed point set, and so this is sort of tubular neighborhood of the fixed point set. And this is a homotopy retract. Tilde, but we are studying Borel-Moore homology that are not homotopy invariant. So the Borel-Moore homology of this and of that are not the same. Okay, so we have this closed embedding, and we have the corresponding map from Borel-Moore homology of S tilde to Borel-Moore homology of S tilde from Borel-Moore homology of BSX.
Прошу прощения, а можете эту камеру повернуть?
Okay, and well, if you remember something about definitions, these are dual to compactly supported cohomology. Okay, now this thing is compact, proper. So the compactly supported cohomology is the same as cohomology itself, but here it's different. So it's not proper anymore, so this map from compactly supported cohomology of this to that is not necessarily an isomorphism, and it's not an isomorphism. The compactly supported cohomology is not homotopy invariant. Yeah, for example, compactly supported cohomology of the affine space, it lives in degree 2n. Okay, if it's complex affine space. But now it's contractible, but the compactly supported cohomology of the point is just C in degree 0. Okay, so it's not homotopy invariant. And the same applies to Barrel-Moore homology. It's just dual of compactly supported cohomology. Okay, so for this reason, this homology is something different. This will be the co-standard module. But this map will be a map from standard module to the co-standard module. Now, if we take some care in choosing this local slice and choose it but it's homotopy equivalent. Yeah, the embedding of the maximal compact subgroup into here is called homotopy equivalent. So in particular, when intersected with the centralizer of a unipotent element, it will have the same component group. So for this reason, then the component group CSX will act on this slice and on its maybe G of SX. Maybe K of SX will act on this slice, but K of SX modulo K naught of SX is the same component group. And so this component group will act on the Barrel-Moore homology of S tilde. And so just similarly, we define the co-standard module. K dual AX chi just as a multiplicity space from this to homology of S tilde. Okay, and just from this construction, there is the standard morphism psi from the standard module to the co-standard module. Okay, now we will have also nameless module L, that is the image. Okay, but secretly this L will be an irreducible representation, and this is the content of the next main theorem. And I'm afraid that the proof of this main theorem will take all the remaining time till mid-December. This is the classification of irreducible representations of affine Hecke algebra. Okay, so just before I formulated one last word, that the centralizer of S and x, or just s, x by conjugation on the pairs of nilpotents and the relevant representations, and the conjugate pairs give rise to the isomorphic K standard models, co-standard models, and the images. Okay, so now the main theorem. This is due to Ginsburg, but somehow he historically his proof was incomplete and even wrong. And as Cardinalistic noticed, even the statement of his theorem was false as stated. Okay, but still, so Cardinalistic independently proved this correct version of the theorem, and then Lustig corrected his mistakes and obtained, well, essentially the same proof, but somehow historically he discovered this proof independently, but only made some minor mistakes. Okay, so the theorem says that the module LAX chi is irreducible. Under the condition that it is non-zero. Sometimes it can be zero. Now, the two modules AX chi and LAX prime chi prime are isomorphic if and only if the pairs X chi and X prime chi prime are conjugate. Now, the second claim is that if T is not a root of unity, so remember our element A was the pair S and T. S was a semi-simple element in our semi-simple group, and T was an element in C star, multiplicative group. So if this extra element is not a root of unity, then this would be irreducible module is actually non-zero for any nilpotent element in the fixed part of the nilpotent cone, and chi a relevant representation of the component group. Okay, but for roots of unity, there are some vanishings, and in fact, it's possible to describe them explicitly as well, but we will not do this. So maybe let me only mention that for roots of unity, it was done by Granovsky, by Ian Granovsky. Okay, and finally, any simple HA module arises this way. Okay, so, well, in a sense, this is a successful classification, though it goes through some geometry of Springer fibers, but still it's manageable. It's possible to combinatorially describe everything that appears here, especially in type A. It was done even long before A. There was a combinatorial classification and it was done by Joseph Bernstein and Andrei Zelevinsky. Essentially around 1980, and this theorem is around 1985. Okay. Maybe I should be more careful. In type A, I mean for G equals GLN. So if in case G is SLN, then it's harder. But for GLN, it's for GLN, all the component groups are trivial. And so, as you see, the combinatorics is simpler. It was done by Bernstein and Zelevinsky without any geometry. If you want to be really rigorous, because I said that G is a semi-simple group, and GLN is not quite semi-simple group, then I should say PGLN. Okay. So one stupid corollary. Since HA is finite dimensional algebra, the number of irreducible representations of HA is finite, and hence the number of centralizer of S orbits in the nilpotent cone fixed points is finite. So it's some generalization of the fact that the orbits of G in nilpotent cone only form a finite set. Certainly one can prove this without going through all this Hecke algebra stuff, but at least we get this. But in fact, already the proof that the number of nilpotent orbits is finite is not very elementary. So we did it in the invariant theory course last year, but it requires some work. Okay. So before we start proving this theorem, let me say a few more words about the standard modules. Namely, it's possible to compute their characters. So first of all, what do I mean by characters? Inside the affine Hecke algebra, we have this big subalgebra. The representation ring of the torus. Yeah, this is Bernstein subalgebra, and inside it we have the center, and we know that this acts by the central character A. But still, this thing may act in a compatible way, but in an arbitrary compatible way. When I say the character, I mean the character as a restriction to this commutative subalgebra. Say K restricted to this. Okay, and well, somehow the question does make sense, and it's very similar to the standard setup in the category O. Yeah, so there you have standard Verma modules. Say M over chi. Dual Verma modules. M dual of chi. And reducibles. L of chi. In fact, there is a standard map from the Verma module to the dual Verma module, and it factors through the canonical surjection onto irreducible head, quotient, L of chi. So this part is all very similar to the Hecke algebra setup, and also the same about the characters. We know that we can fix some central character, the center of the universal algebra of G by Harish-Chandra is isomorphic to the symmetric algebra of Cartan. And then you take invariance of the Weil group. So you see it's all very, very similar. Yeah, I just here I have Cartan-Lie algebra and here Cartan-Torus. Otherwise, just the same. Now we take again some point Z in the spectrum of the center. And if we fix it, then any reducible or Verma module has some particular fixed central character, but still, though it says a lot about its actual character, but not everything. Yeah, if we fix the central character, we don't know what is exactly the character of M and L. Yeah, so for a fixed, say, regular Z, there are W many Verma, well, chi, such that M of chi, M dual of chi, and L of chi have the central character Z. I mean, these chi's are all lying in the same W orbit corresponding to this Z. Okay, and the characters of Verma modules are very simple. Just because the Verma modules are defined as induced modules. Okay, so the character of M of chi, in fact, it's equal to the character of dual Verma module, and it's equal to e to the power chi times the character of the symmetric algebra of the negative Nilpovic subalgebra, and this is some product over negative roots. Okay, so this is well known, but the character of irreducible quotient is something very mysterious. L of chi. So if chi is dominant, then it is given by the Weil-Carter formula or by BGG resolution. So it's some maybe I should write some plus minus 1. Like this. So if I is dominant, and here I mean the dot action that is centered minus rho. Okay, but if chi is not dominant, then it's a very difficult problem to find this character, and it was solved by many people. So it was proposed by Cardinalistic. In 1979, maybe, and proved by Williamson-Bernstein. And independently by Berlinski-Kashivara. Okay, so that again, character of L of chi equals certain linear combination of characters of Verma modules. Whatever. And these are so-called Cardinalistic polynomials. So they are related to singularities of Schubert varieties. B, double B, whatever, Y in the flag variety. Okay, and exactly the same thing happens here. So now I will write down some sort of explicit formula for the character of the standard models over affine Hecke algebra, and then there is another formula that expresses the character of irreducible modules in terms of the standard characters via some Cardinalistic polynomials well, in a similar setup. This I will explain. But what is funny is that the usual Cardinalistic conjecture that was proved by these guys, somehow using D modules on the flag variety. In fact, it has another independent proof that is exactly, well, just somehow repeats the proof of for the affine Hecke algebra case. Okay, so there is another proof of the standard Cardinalistic conjecture for the formula of irreducible characters of universal enveloping algebra. That is just a word for word repetition for the affine Hecke algebra case. Okay, so now let's proceed with the computation of standard characters. Okay. So we have this fixed point sets simultaneous in the flag variety, and let's split them into union of connected components. So we already discussed this in the very beginning today, that the connected components come from the semi-simple element. The nilpotent element, it has very singular but connected Springer fibers. But the fixed point sets of the semi-simple elements there, smooth but disconnected. Okay, and now there is an action of the component group on this set of connected components. And so if some element, say G, in the component group preserves a certain connected component, say Bj, then we can define the Lefschetz number L of G Bj, just the alternating sum of traces on the cohomology groups. Okay. Only, sorry, it's homology groups. I'm sorry. Homology groups, and also we set some pairing. So we will have an element theta lambda in the Hecke algebra. In fact, inside of this T. Inside the Hecke algebra, and well, somehow the character on this element will be written down in terms of this pairing. The pairing with S, and it will depend on the connected component. So this will be the exponent of lambda evaluated at S, taken modulo the unipotent radical okay, so we take a Borel subgroup B inside this particular connected component, and then S lies in this Borel subgroup, and this Borel subgroup projects onto the quotient B modulo its radical or commutant, and this is isomorphic to the Cartan torus, but somehow this isomorphism is in principle it's not canonical, just some isomorphism. But I claim that over a kinetic component, it's possible to choose just one such canonical isomorphism. So this T can be called abstract Cartan. Okay, and what do I mean by this? I just mean that the bundle over Bj with the fiber B modulo its commutant is trivial. Okay, so we can trivialize it, and this is a trivialization. Okay, and it is trivial just because when two elements in here are conjugate with respect to some so if B is the adjoint action of some H on B prime, then somehow the adjoint action of H from B prime modulo the commutant to B modulo its commutant is this isomorphism. I mean, if I change H, then the difference must be in B prime, and then this isomorphism will change by the joint action of the difference on this commutant, but the joint action on the commutant is trivial. Okay. So, for example, for this reason, if I take S, for example, and X all trivial, then I have the whole flag variety, and on the whole flag variety, this bundle with fibers B over the commutant is again trivial, and this the fiber is called the absolute Cartan group, but it's rather not a subgroup, but rather quotient group B over the commutant. Okay, but this here we choose a trivialization for each kinetic component separately. So since the flag variety as a whole is connected, then there is this abstract Cartan for the whole flag variety, and for each kinetic component of the fixed point set, we have to choose its own trivialization. So we only have this notion separately for each kinetic component. Okay, so all in all, we have defined this pairing. Well, maybe I should say one other thing, that if S is regular, then as we noticed in the beginning today, the fixed point set is the same as fixed point set with respect to the whole torus containing S, the centralizer of S. And this is just the union of points numbered by the while group. And this pairing will be essentially something like this. Okay. So we're still trying to write down some formula for the character of standard modules, and now we're almost there. Okay, so it says that the trace of the element theta lambda in the standard module, okay, a x chi is equal to 1 over the order of the component group, the sum over these connected components, and then for a connected component, you take the sum over the stabilizer of this connected component. So it lies in the component group. Okay, and then you take the trace of the character of trace chi g times the Lefschetz number and times this pair. Okay, so this should be viewed as an analog of the simple formula for the character of Verma module, but it is not as simple because you see it uses some geometry of flag variety and fixed point sets, but otherwise everything is pretty simple. Yeah, for example, this element, well, this also uses the connected components of fixed point set, but still it's rather elementary. Okay, so let's prove it. And certainly the homology of the fixed point set, this is the underlying space of the standard module, well, up to isotypic decomposition, yeah? There's the sum over orbits. Of the component group in this set of connected components. And that is the sum of induced representation from the stabilizer of a component to the whole component group of the homology of this particular component. Yes. Mm-hmm. I mean, G is an element of the stabilizer. This is a subgroup, and what's the question? Yes. So these are just connected components of the fixed point set, and G is presumed to stabilize this particular component. So it acts on it. Yeah. Oh yes, certainly yes, but then certainly it is homotopy invariant, and in a connected component it does not change. So it's independent of the element of the choice of element in a connected component. So it's well defined for a connected component. For any irreducible representation, we have the multiplicity space of this type chi of the induced representation equals multiplicity space of the restriction over this subgroup, the stabilizer, to the homology of the component, and the action of theta lambda. If you remember somehow the long construction we went through, the action of this commutative Bernstein subalgebra was very simple. It was defined just by multiplication by certain the corresponding line bond. Okay, so the whole proof of this big Ginzburg theorem was by explicit construction of generator's action and then checking relations. Yeah, and the generators were of this sort, and then the action was simple just by twisting by line bundle, and also the standard generators of the finite Hecke algebra, and then it was rather complicated. Yeah, convolution with some vector bundles on the projective lines or something like this. So the action of this part is just multiplication by the line bundle of lambda. And now we act on this particular fixed point set, so we just restrict it to the fixed point set. And now if we consider first the fixed point set with respect to the semi-simple element, then as we discussed, this is the union of connected components, and the connected components are all isomorphic to flag varieties. Of the centralizer group. Okay, and the yes. Pardon me? Yeah, you see here the groups are finite. Yeah, there's the finite component group. So it's both left and right adjoint. It doesn't matter. All the representations are semi-simple, so it doesn't matter absolutely. Okay, so now we had our group A inside G that was generated by A. So the connected component, this was a torus, and it was an abelian subgroup, and the action on the fixed point set Bs is trivial, but the action of this group on the line bundle factors through the action, just the fiber-wise action, the dilation action on the fibers. Via some character from A to the multiplicative group, and we want to compute this character. Maybe let's call it lambda I, because it depends on this kind of component yi on yi bs. Okay, and then I claim that this lambda I is just this pairing. For any component B J inside yi. Okay, so we have Bs, it contains Bsx, this is the union of Bj, this is the union of yi. So each connected component here is contained in the connected component here, and we have such a such an equality just from definition. Okay, and then we have to compute the action on the equivariant K-theory of this component. Again, because A does not act on yi, this is just the product of representation ring of A and non-equivariant K-theory of y. And from this, the class of the line bundle preceded to yi is just the product of exponent of lambda I in this part, because the action factors through just this character lambda I of the group A. And times the class of O lambda on this component. And okay, so they are just elements in here. And then we have to specialize. HA was the specialization of our K-theory when we specialize this to A, to the point of spectrum of this guy. So after this specialization, we get the isomorphism with just non-equivariant K-theory of y. Yeah, just because the action is trivial. So say this. and we get just non-equivariant K-theory of yi. And then, if you remember how we identified the specialized K-theory, the central reduction of the Hecke algebra with the Borel-Moore homology, then we had to take at this point the Chern character to Borel-Moore homology of yi. And if we now take this element in here and go all the way through, then this element goes to this pairing number j on the bjth component times the Chern character of O lambda restricted to yi. Okay, but the Chern character is an element of the sort 1 plus something in the higher cohomology. So this is a unipotent operator. And it does not change the trace, the character. So essentially, the trace will be just this times the dimension. Okay, so now I will use it, but I have to erase this formula, so maybe have a last glance on it. Okay, so from here we see that for any theta lambda invariant subspace V in the homology of connected component, the trace of theta lambda on this space is just this pairing times dimension of V, just because the correction Chern character is unipotent. Okay, and now we just rewrite this formula I just erased. So the trace of theta lambda on the standard module equals the sum over orbits of the component group in the connected components of this pairing times dimension of Holmes over the stabilizer subgroup, character of chi restricted to the stabilizer subgroup, and the homology of the connected component. Okay, but dimension of Holm is given by the scalar product of their characters. I mean, you have to take the trace of this times trace of that complex conjugated and pair them in the group ring of our finite group. But then the action on the Borel-Moore homology has integral characters. Yes, so they are not arbitrarily complex numbers, but just integers. And in particular, they are self-conjugate. And I don't have to take this extra conjugation. So what I get is the sum over J, then the component group order inverse, and then I take this pairing lambda s and the sum over elements in the stabilizer, the trace of chi of g, trace of g on the Barrel-Moore homology of the component. Okay, and that's it. The only problem is why this is equal to the Lefschetz number. Because in the Lefschetz number we took the alternated sum, and here it's the total trace. So here are some negative signs, and here are some, all the signs are positive. But the point is that all the Barrel-Moore homology appearing here only live in even degrees. Okay, so there is this equality since there is no odd Barrel-Moore homology. Okay, and this is a difficult theorem by Cardinalistic de continuat procesi, but it's true. Okay, so this is the computation of the character of standard representation, and maybe in a couple of times we will write down the character of irreducible representation and also prove that it's really irreducible. But to this we will, to this end, we will need to use some constructible sheaf theory to compare it with Barrel-Moore homology. And so I have to recall some basics of constructible sheaf theory. So I apologize to most of you because you heard this last year. So you're welcome to leave now. I will just repeat what I said last year about constructible sheaves. So it's sort of, it's called Shrikology. And the terminology is due to Ed Spitz. And this is because the standard operations on constructible sheaves are the push forwards, the pullbacks, the shriek push forwards, shriek pullbacks, and also external tensor product, and also an internal home. Probably that's it, but there are some more. So what are constructible sheaves? So first of all, they are local systems. And these are the same as locally constant sheaves. And they are combinatorially described as representations of fundamental groups. So is it clear to those who did not attend last year, the locally constant sheaves are the same as representations of fundamental group. Well, say Vanya. First of all, I hope you know what is constant sheaf. And locally constant sheaf is locally constant. And then it gives rise to representation of a fundamental group just because if you have this base point x and you have a loop, like this, then if you go around this loop, your sheaf is locally constant. So its stocks at nearby points are identified. Okay, and the stock at x is identified with the stock at some nearby point. And then there is another point near to that one, and so on. And all of those are identified, but when you come back, globally, you may have acquired some monodromy. Fine, but if you slightly move this loop, nothing changes because again of this local constancy. So it depends only on the homotopy class of this loop, and this way you get for any locally constant sheaf f, you have a representation of the fundamental group. On the stock at point x. Okay, and conversely, if you have such a representation, then you can construct a local system with this action. And can anybody explain how? Yes, Grisha? Absolutely, yes. So you take x tilde, a universal cover. Yes. Take the constant sheaf here. Okay. Yes. With this representation, say rho. Okay, so it's the converse construction. Okay, thank you. So the constructible sheaves are called constructible because they can be described somehow pretty economically. Like if they're local systems, you need only just one representation of fundamental group. Typically, to describe a sheaf, you need much more data. But for local system, just one representation of one group. Okay. So now a sheaf is called constructible. If there is a stratification X, the union of strata, such that the restriction of F to any stratum is local system. Okay. And I will say in a moment why this is also a constructible notion. I mean, why you need only a reasonable amount of data to describe this. But let me say right away that this class of sheaves is closed with respect to the standard operations. And also, if you take higher direct images, okay. So you may also say it in the following way: you start with local systems, but then you consider all the possible morphisms from X to Y. And you take a local system here, but then you take its direct image or higher direct image to the base Y, and there you obtain something more advanced, some stratification and locally constant sheaves on the strata of this stratification. So you start with local systems, then you close it with respect to the push forwards and derived push forwards, and you obtain all the possible constructible sheaves. So you want to obtain some class of sheaves closed with respect to standard operations. So you start with local systems and you close it, and there you are. How do you describe this? So they are obtained by Artin gluing. So you need local systems. And we know that this is the same as representations rho S of fundamental groups of strata. But also you need some relation between them. Yeah, you have to somehow glue the things on various strata. So suppose you have one strata in the closure of the other, like XR lies in the closure of XS. And then you can take a tubular neighborhood like U R of XR in the closure of XS. So certainly it's it contracts back onto UR. But inside you have some punctured neighborhood, namely this punctured UR is the intersection of UR and the stratum, the open stratum XS. Okay, and then it certainly embeds into XS. Okay, and you have the fundamental group by one of so let's assume that the base point for this bigger stratum lies very close to the smaller stratum in its tubular neighborhood. Sorry. Okay, then there is a morphism from the punctured tubular neighborhood fundamental group to here. On the other hand, it projects to the fundamental group of XR itself, like this. And we have a local system here. So there is a representation of rho S, rho S on some space Vs, the nearby stock, and also this acts by rho R on VR, some stock in the smaller stratum. Okay, and now I claim that there is some compatibility between those two representations somehow via this correspondence of fundamental groups. Namely, there is a morphism from here to here. And this because, well, let's say this is the smaller stratum, the smaller point, and this is the bigger stratum, and there is some nearby point. This is XR, this is XS. Then certainly you have a so-called co-specialization morphism from this smaller stock to the bigger stock. Yeah, just because the smaller stock is by definition the sections on some neighborhood here, and then you can restrict it to this section on this neighborhood. You can restrict to the nearby point. So there is this co-specialization morphism. So again, I'm using the fact that our sheaves are locally constant and that my base point here is close to the point here. So there is this co-specialization morphism, and then it is compatible in the sense that it should go to the so how should I say this? Well, there is a composed representation of this group, but on the other hand, there is a composed representation of their group, and they should be the same. Okay, so the compatibility is that the two, let me call it PS, and this PR. Okay, so then rho S composed with PS is the same as co-specialization composed with PR composed with rho, sorry, no, composed with rho R composed with PR. Yeah. Yeah, this is true. Okay, so this is the Artin gluing for the constructible sheaves on a stratified space. So you see that it's again some in a sense finite amount of data to describe such a sheaf. Okay, and then next time we'll consider complexes of such sheaves and operations like this on the complexes of these sheaves. Thank you.